Okay, so now we are on to our new journal. So this journal is called Graphing Log Functions, and you're going to figure out why here in a sec. But let's get started here with our bell work. So this bell work here is just asking you to solve for x, and what we have here is 2 raised to some power x gives us 8. Can anyone guess what this is? Well, x, some of you might already know, x has to be equal to 3, right? Because 2 to the 3rd power gives me 8. We've seen this multiple times, right? 2 times 2 times 2 gives me 8. So, what if I change the game here? What if I asked you what 2 to the some x power equals 7? So what power for 2 would give me 7? Now, some of you might be a little puzzled, right? Because I know 2 to the 3rd power gives me 8, 2 to the 2nd power gives me 4, but it doesn't look like a whole number as an exponent gives me 7, right? So I know that this exponent here has to be between 2 and 3 because 7 is between 4 and 8. And that would give me a decimal number, right? And we wouldn't know for sure what that exponent would be in decimal numbers. We would have to do a trial and error kind of thing. So what we're going to be learning today is how do you find exponents when you're given the value already and the base. So in mathematics, we have learned that a lot of different types of operations, right? We've learned that to undo adding, we use subtraction. Multiplication is undo by division. So we've learned a lot of different inverses of operations. We've learned about powers, right? If x is to some power, we can undo that power by taking the root, right? So we've learned a lot of different types of inverse operations. So if we learn an operation, we learn the inverse of it. So we've learned about exponents, so some base to some power. And now what we're going to do is learn how to figure out what the exponent is. But what does that look like? What do we use to undo exponents? Well, that's all about today's lesson. So we're going to talk about something called logarithms. So stay tuned for the next slide. All right, so we're going to be talking about logarithms. And logarithms, or sometimes we just call them as log for short, is an operation we can use to get to an exponent form. So logs and exponents are inverses of each other. So logs show the relationship of an exponent. All right, so let's talk a little bit about these here and how they're related. So if you notice here, this b, the little small subscript here, represents the base of your exponent. So we call this base. A, which is usually what the value is when you take the exponent of the base and get your value. So notice that that value here is next to the subscript, that b there. So this here, your a, is your value that you get after you take an exponent or after you take a power. And notice on the other side of the equal sign for the log is your x. And what is x? Well, if you look back at this here, x is your exponent. So what this means is that when you are given the base and you're given the value, you can actually find the exponent when you take a log, which is good because that's exactly what we want. If we had a problem like the one we previously had, 2 to the x power equals 7, well, if we had the base, which was a 7, and the base was 2, and the value was a 7, which is your a, then we can calculate the exponent. Now, before we get there, let's just learn how to use logs from switching them from logs to exponent. That's what we're going to be focusing on in this journal. So to rewrite a log to an exponent, let's try to do that with part A here. So here I have log 232 equals 5. So first, I'd ask myself, what is the base? right? So the base here is this 2. So I'm going to do some labeling here. So this is my base. 5 here is my exponent, or my x, you can think of it if you're referring to this formula. And the 32 here is your a, or your value. So if you were to rewrite it like this formula, you would have to do b first, which is your 2. Then your x looks like it's next, so x is 5, equals the 32, which is your a. So all I did was label what the numbers meant on the log, and then I wrote it in this format, the exponential format. And notice that I just went from a log to an exponent. So this here is my answer. Now, if you didn't like that way where we label it and we wrote it out as an exponential, there's also a little trick you can do. It's called the heart log hack. And so what you have to do is, if you have a log, let's use that same formula, log BA equals x, you can change it to an exponent by drawing a heart. This is what I mean. You start with your base, and you go to your x to curve and make a heart, and you land on your a. So when you do this motion, notice you start with your b, then you go to your x, or your exponent, and then you go to your value, your a. And when you do this, you actually go from b, x, and that equals your a. And so that there is your, you just change this log to an exponent. So that motion b to x to a writes it out as b to x to a. So I'm going to try that heart hack on this part B. So I'm going to go from 2, actually let me do this in a different color. I'm going to go to 2 to negative 1 to 1/2. So this is 2 to negative 1 equals 1/2. I'm going to do this again with the part C. So I'm going to go from the base 10 to 0 to 1. Make my heart. So this is 10 to the 0 power equals 1. Which makes sense, right? Anything to the 0 power equals 1? All right. So now that we've gotten a little taste of rewriting logs to exponents, let's go backwards now. Let's take an exponent and write it into logs. So we're going to do that here in the next slide. Okay, so now we're going to write them as exponents to logarithms. So I'm just going to write that equation above here that we just saw a moment ago. So if I have a log with a base, sorry, that should be a b, a equals an exponent, then I can rewrite it as bx equals a, or as an exponent. So if I already have an exponent here, right? Well, first I have to ask myself, what is the base? Well, the base is my 15, because that has the exponent on it. So my 15 is my base, so that's my b. The 3 is my exponent, so that's x. And this big number here is my value, so that's a. So if I write this as a log, and I'm writing from left to right, so this is going to be log my base, which is 15, my value, which is 3,375, equals x. And so now I have my, my exponent written as a log. So you can use this labeling method where you figure out what is your base, what is your exponent, what is your value, and then put it together as the log description. Or you can actually try to use the heart trick. So what you would do is you would start with your base, just like you did before. You would swing it to your value and then your exponent. So this is the log of your base, which was 6. 1 over 36 equals -2. And you can rewrite it that way. So if I do that with C, just watch. I go from the base to the exponent to the, sorry, not the exponent, the value to the exponent. So this would be log 27, 3 equals 1/3. And that's it. All right, so now that we've talked a little bit about logs and how to rewrite them as exponents, now we're going to learn how to graph them. And we actually, what we do is if we're given a log function, like this one here that we have, in order to graph them, we write them as exponents first and then try to graph them. because that's a lot easier to do because we know how to graph exponential functions. So how do I write this as an exponent? Well, first off, generally when we're rewriting it, the log is on the left side of the equation, whereas the exponent is on the other side. So if you're used to the log being on the left-hand side because you want to use the heart method to try to rewrite this as an exponent, feel free to do that. So what I mean is, if you need to write it as log 5x, where log is on the left-hand side, and then do your heart, feel free to do that so that way you can rewrite it as 5y equals x. So now that I have it as an exponent form, I'm going to try to graph it. So if you remember exponents, the general function for an exponent, let me write that here. So for exponents, it's a, your coefficient, b to the x, which is your base, plus k. So the k, remember, is your asymptote. So when you're looking at this equation here, here's your base to an exponent. Does it have a k? Or does it have a plus anything or minus anything on the side of it? No. So our asymptote here, it looks like at 0. Okay, and so now from here, we're going to try to plot some points. So just like how we've done before in the past, we're going to make a table. We're going to pick a few points. So we're going to pick some x and y points. But this time around, take a look at the equation again. The y here is your exponent, right, instead of x's. So in this case, this time I'm going to choose values for y instead. So I'm going to choose those same values. I like to choose -1, 0, and 1 because they're easy to plug in. So I'm going to plug those values now into the y, because when I plug them in, I'm going to get my x, right? So let's do that. So to the side here, let's plug in some values. So I have 5 to the -1. What is 5 to the -1 power? That's just 1 over 5. Or if you put that in a calculator, that's about 0.2 as a decimal. Let's see. 5 to the 0 power, if I plug in 0, is just 1, so that's just 1. 5 to the first power, if I plug in 1 into this equation, is just going to be 5. So this is just 5. And so I have my points now. So I'm going to go ahead and plot them. So that's going to be at 0.2 for x. So that's between 0 and 1 for x. So it's about right here, but down 1. It's about right there. And then 1, 0, 1, 0 is about right here. 5, 1 is about right here. And then I'm going to do my best to curve and connect the dots. But hold up a minute. Isn't the asymptote here 0? And so a horizontal asymptote would be right here. Let me highlight that if I had to draw a horizontal. A horizontal asymptote would be right here. But the thing is, this point, the way we plot it, crosses, and if we connect the dots, crosses the horizontal asymptote, which can't be possible, right? But I did the table correctly and I plotted the points correctly, so what's going on, right? Why am I crossing the horizontal asymptote? Well, it turns out, because this originally was a log function, this is actually not a horizontal asymptote. This is what we call a, let's see if I can undo that highlighting there. So this is actually what we call a vertical asymptote. So I'm going to write that here. This is a vertical asymptote. So what does that mean? It just means that the asymptote doesn't run side to side. It runs up and down. So this vertical asymptote is actually on the x-axis now. So like you're going to go to the x-axis and you're going to go to x equals 0 instead of y equals 0. You're going to go to x equals 0 and draw a vertical line. So I'm going to highlight the vertical axis, which is right here. And it's at x equals 0. Okay? And so what this is going to be is that this curve is going to get really, really close to the vertical asymptote, but not touch it. Okay? So you're going to do your best not to touch that vertical asymptote or when x is equal to 0. And so just like before, like horizontal asymptotes, vertical asymptotes, the curve is going to get really, really close to, but never touch and never cross. So there we have it for logs. Because they're inverses of exponential, they're going to have vertical asymptotes instead of horizontal ones. Now, if we take a look at answering some of the other problems here, this x-intercept looks like it's at 1, 0. So for x-intercepts, that's when your y equals 0. So notice that I chose strategically that y was going to be 0 to get my x-intercept. So I got 1, 0 for the x-intercept. And then if I'm looking at the domain here, because of the vertical axis, this limits the curve from going any further left, right? So it looks like I'm going from 0 to positive infinity. So this curve can only go from 0 on the x-axis to positive infinity. So this is from 0 to positive infinity. And I'm going to use parentheses because one side is, well, this side here is a vertical asymptote. So it's going to get really, really close but never touch 0 for x. And this side here is getting to positive infinity. And for the range, that's looking at the y-axis. Notice that this curve points down towards negative infinity. And this side here, there's nothing stopping it from pointing up. So this is going to actually increase. So this curve is going to positive infinity. So in other words, the range is all real numbers. Notice how the domain and range are switched with logs. Remember how exponentials, the domain is all real numbers? Well, now for logs, the range is all real numbers. So, quick side note, for all ranges, so the range for all log functions are all real numbers, whereas the domain for all log functions uses parentheses. So there we have it. We have just graphed a logarithmic function. So two things for a log function here. Whenever you're given a log function, you have to change it to an exponent function. And then the same process is done. And also the horizontal asymptote is now a vertical asymptote for a log function. So let's try some more problems here. 2 is negative. Okay. All right, so now we're going to take a look at a second problem here. This time around, you'll notice that I actually have the y here instead of y. It's f of x. And most of the time, you're going to see it as f of x. F just means function. And so in order to graph this, remember, we have to rewrite it as a exponent form. So it might be easier to change this to a y first, so that way you don't rewrite it a dozen times with f of x. That's a little, a lot of writing. So we're going to change this to y, and now we're going to change this to an exponent. So how did we do that? Well, you can use that heart trick. So if you want to use that heart trick, you would just need to rewrite this as log base 4x plus 2 and put the y on the right-hand side. So when you do this, make sure that the log is on the left-hand side, and then you can do your heart. So it goes from the 4 to the y to the value. So this is 4 to the y equals x plus 2, and I just dropped the parentheses because I don't really need them. You only really need parentheses when you're raising it to a power, and this is not to any power. It's just 1, so it's just itself. Okay, so now what we're going to take a look at is this equation here. So before we can graph this, it's really important that x is by itself. So in order to get this x by itself, I need to get rid of this 2, so I need to subtract by 2. And I'll show you why here in a sec. So this 2 will cancel out, so I just have x. However, this side here, this is what the biggest mistake people will do. They will take this 4 and subtract it with this 2. But you can't do that, okay? That's a big no-no. This 4 has a power y, and this is an exponent. You cannot take an exponent, an exponential part, and subtract it with a constant. So they are not like terms, so we just bring it down. So this is really just 4y minus 2. So now it looks like this x is by itself, so this is good. I'm going to use this and box that in to say that this is the equation that I'm using. And so when I look at this, I notice that I actually have an asymptote this time, right? Because if you didn't move that 2 over, you might be neglecting to see that this equation, this exponential function, has an asymptote at -2. So that's why it's really important to get that x by itself. So next thing, I'm going to fill this out. Remember that range for logs are all real numbers, so I'm just going to fill that out. And so now I'm going to make a table. So x and y's, and I'm going to make this, let's see, -1, 0, and 1, right? Because that's the values that Ms. Chang always chooses. And so now we're going to plug this in. Okay, so here I go. If I plug -1 into this y here, I don't know why I just wrote a y. Let me erase that. So I have 4 minus 1 minus 2 equals x. So 4 to the -1, that's just 1/4. Remember, negative exponents means that you put in the denominator, or you can think of it as a reciprocal. And 1/4 is really just 0.25 as a decimal. I'm subtracting that by 2. If I subtract that by 2, that's really -1.75. So when you plug in -1, you get -1.75. So now I'm going to plug in 0 into this equation. So that's going to be 4 to the 0 power minus 2 equals x. Okay, 4 to the 0 power is just 1. 1 minus 2. Okay, 1 minus... so 1 minus 2 is just -1. So x is equal to -1. And last but not least, I'm going to plug in that 1. So 4 to the 1 power minus 2 equals x. Well, 4 to the first power is just 4. Minus 2, well, that's just 2. And so x is equal to 2. So now I'm going to go ahead and plot those points. So I have, let's first draw that asymptote. So this asymptote here is at -2. So I have to go to the x-axis and draw a vertical line. So right here. So I'm going to actually do a dash line. So I'm going to do a dash line through that -2. And this is my vertical asymptote, so I'm going to call that VA. And I'm going to plot my points now. So it's at -0.75. So that's like really close to -2, but not quite. And it's down at -1 for y. And then the next one's -1, 0. So that's like right here. And then 2, 1 is about right here. And I'm going to try to connect the dots. So notice that this side of the curve is getting really, really, really close to the vertical asymptote, but not quite. And actually, something I want to mention here. Whenever you're drawing that curve, let me actually redraw that curve. You should think of the curve and the vertical asymptote, or any asymptote, being like magnets. They attract each other. So when you're drawing this curve, you want to draw like it's attracting this, it's being pulled in by the asymptote, the vertical asymptote. But it's still being kind of repelled a little, because in a way, you remember, vertical asymptotes you can't touch and it can't cross over. So the curve should lean towards the horizontal or vertical asymptote, but never touch it. But it still should lean towards it. And let's see if we can answer some of these questions here. So the x-intercept we calculated here, that's when y is equal to 0, so that's -1, 0. -1, 0 here. And the domain here looks like this curve doesn't go further left than -2, and on the right side it keeps going on and on forever, so that's to infinity. So we're going from -2 to infinity. And that's it. Okay, so now we're going to take a look at this function here. So the first thing I'm going to do is switch it to y's, and then rewrite the equation. And if you take a look at this problem here, the log has a base x minus 3. So if you remember the equation from the last problem, it was y equals, what was it, log 4, but it had parentheses, x plus 2, right? Notice that you can see what your base is, which is 4, and your value here is x plus 2, and it's all encapsulated in a parentheses, whereas this one doesn't have parentheses. So that means that this 3 here, this negative 3, is not really attached to this log. It's not, the log is not in, the 3 is not with the log, okay? So in other words, when I see this problem here, it's saying log base 2, but just x. So those parentheses are implied that just the x has the parentheses. This 3, this negative 3, is actually outside of the log. So just like square roots where you need, if you ever want to take, if you have a square root and you want to get rid of it, you have to make sure the root is by itself. Well, logs are the same way. If you want to solve for logs, you have to try to get the log by itself first. So in this case, if this is our log, let me grab a highlighter, right? What needs to be removed? Well, it's the 3. So we have to add 3 to both sides. So that cancels. So I have y plus 3 equals log base 2x. So now that I finally have the log by itself, I can switch it to exponent form. So this is really going to be, actually let's write it in that where log is on the left side first. So that way you guys can use that heart trick if that's your preference. So if you write log on the left side, if I do my heart trick, this is going to be 2 to the y plus 3rd power equals x. So when I look at this here, once I've translated to an exponent, you have to make sure x is by itself. And in this case, it is. So this is my equation. So I'm going to box that in. And based off the equation, is there a asymptote? No, because this exponent here doesn't have like a plus or minus k next to it. So in this case, I have just 0 for my asymptote. So I'm going to go ahead and highlight that region. That's my asymptote. Remember, it's on the x-axis because you're drawing a vertical asymptote. So in this case, here's my vertical asymptote. And so when I draw the, before I get ahead of myself, remember that the range for all log functions is all real numbers. And now we're going to make the curve. So to make the curve, we got to make our table. I'm going to choose some y values, and now I'm going to plug them in. So these are the y values I typically choose. I'm going to plug it in for y and see what I get. So I have 2 to the negative 1 plus 3 equals x. Now, I can already see this, but maybe some of you can too. When I chose these y values, they might not have been the best y values to choose because the exponent is still going to be very large, which makes the overall number large. So what does this do to the graph? Well, not much, other than you might have to extend your coordinate system in order to accommodate the large numbers. Now, I'm okay with this. Now, for some of you who are more strategic thinkers, you might want to think of smaller numbers that make this exponent smaller. Now, for me, I don't care that much. I like to plug in numbers that I'm used to plugging in, so negative 1, 0, and 1. And then if I have to adjust my coordinate system, I'll just adjust it later, because that's just easier for me. So if I go back to the problem here, I'm going to reduce this exponent. So negative 1 plus 3 gives you 2 to the 2nd power. 2 to the 2nd power is just 4, and so this is 4 here. Now I'm going to plug in 0, so 2 to the 0 plus 3 equals x. 0 plus 3 gives me to the 3rd power, so 2 to the 3rd power. 2 to the 3rd power is 8. Notice that my x value that I got was 8. So just like I was saying before, because the exponent is a little bit larger now, I get an overall larger number. And notice my coordinate system only goes up to 6, so I need to probably extend this coordinate, which I will here in a sec. So just going back to the problem here, let's see. Let's plug in our last number. So 2 to the 1st power plus 3 equals x. So this is going to be 2 to the 4th power. 2 to the 4th power is 16. So this is 16 here. So if I were to graph this, for negative 1 is right here. But for the graph, to graph 8, I'm just going to mark it as 8 here and then mark 16. Now, you don't have to do this by scale as long as you make some marks on here. Let me actually do that in black so that way it's different. So I have 8 plotted and 16. So on the graph here, I'm going to 8, 0, and 16, 1. So when I connect the dots, I get a curve like this. And this is the part where people will often mess up, okay? So what I see is that when people are graphing this, like they do this part right, they connect the dots right, and then they'll just kind of swish it down because that's what they're used to seeing. Well, because there's a vertical asymptote here, remember how I was saying that the vertical asymptote and the curve were like magnets? That means that the curve is going to will kind of lean towards the vertical asymptote. So when you draw your curve, you want to try to draw it like it's being attracted to the vertical asymptote but not touching it. And so notice that the curve will lean against it but get really close to that, x equals 0, but not quite cross over it. Okay, so now that we have our graph, let's fill in a few things. So our x-intercept here looks like it's at 0, 8. So I'm sorry, 8, 0. And our domain, well, it looks like our furthest thing to the left for this curve is 0, and then it's going to infinity for the x on the right-hand side. So this is from 0 to infinity. And that's it.